1874, famed adventure writer Jules Verne wrote, "I believe that water will one day be used as a fuel, that hydrogen and oxygen, which constitute it, used alone or simultaneously, will provide an inexhaustible source of heat and light of an intensity that coal cannot have." For a long time, many have thought that hydrogen, the most abundant element in the universe, could hold the key to a clean, sustainable, and equitable energy future. Nearly 150 years later, our planet faces a climate crisis, and we must take action to turn fantasy into reality. Department of Energy Secretary Jennifer M. Granholm announced the Hydrogen Energy Earthshot to accelerate breakthroughs of more abundant, affordable, and reliable clean energy solutions within the decade. We know that hydrogen can reduce greenhouse gas emissions, particularly in hard-to-decarbonize sectors such as industry, heavy-duty transport, and enable energy storage. The goal of the Hydrogen Shot is to decrease the cost of clean hydrogen production by 80% to $1 for 1 kilogram in 1 decade, or 111, to unlock new markets for hydrogen and enable decarbonization across sectors. Like the moonshot before it, we are setting aside our fears and choosing to tackle this challenge not because it is easy, but because it is hard. We hold on to the same spirit of adventure of those who came before us in this mission. Can artificial intelligence and machine learning help us uncover the most promising pathways to achieving the Hydrogen Shot goal? Our team is fearlessly exploring the depths of scientific knowledge and using new and advanced techniques to find connections between exciting new materials, methods, and systems to help us understand their potential impact on the cost of hydrogen production. I am so excited to introduce our team with the heart of adventure, the Hydrogen Discovery Engine.
Thank you so much. So I'm Joseph Wiggins, and this is the H2 Discovery Engine team. So what will, the first thing I want to start on is just looking back on some of the grand challenges of the past and the great things that we've been able to achieve, especially through the use of fuel sources like hydrogen. And this new generation has a new set of grand challenges, one of which is the Energy Earthshots that was established by the Department of Energy. And one subcomponent of that is on hydrogen specifically. And there's this really ambitious goal to reach $1 for 1 kilogram of hydrogen in the next decade. And there's a tremendous potential in this idea to have a green, like a green resource for energy with what would be called like green hydrogen. But currently, this is not the reality of hydrogen. So currently only about 4% of hydrogen that is produced is considered green hydrogen, with the majority of it being considered blue hydrogen, which means that CO2 is created and stored, and then 46% being gray hydrogen, meaning that it's emitted into the atmosphere. And the reason for this is truly an economics problem. So we have, there's a lot of research being done, but it's still not feasible to go 100% with the green solution and be reaching our economic goals. And so what the Department of Energy is really faced with here is a multi-pronged iterative problem where they have to make funding choices that are going to help innovate in this space. Then that's going to influence novel innovations that they need to be able to observe. They then need to be able to assess the opportunities for cost reduction and then let that affect the funding choices in that next phase. And even over the last few weeks, you can see on the right, there's been so many innovations in hydrogen, and this is, I think, within 3 weeks. These are just some huge things about using capillary action to improve electrolysis design and to store hydrogen in an entirely different way, making it into a powdered form versus a gas. And so our team tackled this problem of trying to help the DOE make better decisions using natural language processing and graph neural networks. And we're excited to show off the tool, the H2 Golden Retriever. So the idea is that it can help dig through all this data that's coming out and kind of help spotlight things that'll be important for what we should fund in the future. So the one important thing about our design is that it heavily has the human in the loop. From the very beginning, we've been communicating with the Department of Energy, and they've been a tremendous asset in helping us understand what is the current state of hydrogen. And through that, we built these representations of their knowledge and expertise and what they thought was important, encoded that into ontologies, and then gathered up other things about economics and organizations, feeding all those into our natural language processing units and generating knowledge graphs. Those look a little something like this, where we take a paper and instead of it just being something you have to read, it kind of blows out into its connections with other materials and things that it mentions and metals that are important for the process it's talking about. And these are automatically extracted. One of our researchers spent the 8 weeks reading nonstop, and he probably got through about 500 pages. When we were finished with this over one night, Alushla and I ran this set over around 20,000 pages, and we woke up, it had, processed it. And that opens a lot of doors. So now we have all this data that we're, able to ingest. And we feed those knowledge graphs into graph neural networks to help us understand how thorough are these papers, how should they be ranked and presented in the UI, and then given to the experts. And then finally, there's a concept called the causal decision diagram, in which we try to help visualize actions that they can take, and then potential outcomes it would have on the cost, all in order to reach this 1-1-1 goal. So the tool is live. We're still iterating on it. There's 4 pieces I want to highlight in today's talk. So we have a semantic web that we're going to go over, an ontological view, a component cost breakdown, and then an investment modeler for this 1-1-1 goal. And I just want to mention that the items 3 and 4 were done with the help of psychologists from SFU in Canada, and they've been a tremendous asset. And so let's say that you wanted to know about catalyst cost optimization. If you typed it in the tool currently, this is what would pop up. And so in the middle, you see the concept, and then you see how it kind of shoots out and connects with all these other concepts that are important, like an electrolysis machine, such as the membrane. And if you click on that, you can actually explode out the papers and see what is what papers currently have those concepts in it. This also allows you to look at things that are not heavily researched at the moment. For instance, catalyst-coated membranes are much smaller in comparison to say like the standard membrane, and yet they're a very promising approach for optimizing this. So these sorts of visualizations help the experts kind of understand where the research is flowing and how it's changing. Secondarily, we were working on how to use the research knowledge to help both scrape, order, and sort the data. And so in kind of a phase 1, we come up with a diagram like this, where we're understanding how pieces are connected and sort of the physical components are built. And then that evolves into like a landscape like this, where they can kind of zoom in on the physical system. And let's say you want to look at these catalyst-coated membranes inside the cells, and you kind of zoom in piece by piece, and you can find the papers connected to specific components. We also really interested with the costs. So we did a lot of work on, looking at where are the costs in the system. Not all pieces are costing as much to create these. And if we are, going to make this affordable, we have to really tackle those high costs. So we represent things like the actual cost in the current system by thickness. And you can blow those out and look at what subcomponents are truly holding up that progress towards that economic goal. And then finally, we model things about cost projections. So how much do you think things are going to change? What are the things that you can invest in, and what papers are currently like focused around that topic? And then finally, how might that affect kind of the cost futures? So how is that getting us closer to that ideal goal? So the H2 Golden Retriever has all these components kind of brought together into our interface. And like I said, heavily we talked with the DOE. We brought this to them and did a series of workshops. And together we were able to come up with some really interesting ideas about how we could advance this and use AI in different ways, such as trying to reduce down information to critical components, combine different parts that are promising and look at research that's innovating in those spaces. And then also think about what concepts are staying in academia versus moving into, say, into the industry. As we end this, I just want to thank my whole team, a bunch of individual components that, when arranged in just the right way and given a little bit of energy, produce wonderful insights and knowledge. Thank you so much.